Geometric sequence.
Alrighty, front page. Yesterday you had to do some recursive arithmetic sequences. So I want you to look at your formula for recursive arithmetic. What is the only thing that we really are doing? Well, I should say there's two things, but one of them doesn't even require basically any thinking. But what is the one important variable that we have to find if we want to write an arithmetic sequence recursively? D. That's it. If you want to highlight, I will tell you the thing that's most often forgotten about recursives is that you have to give them the first term. So if you're thinking, I'll probably forget that, you could highlight that too. But like I said, the only one that's going to require any thinking on our part is finding D. And that's what we're going to put in for that recursive formula. Now keep that highlighter handy because as we talk about geometric today, we're going to put those new formulas in there. And we want to keep track of what we have to find in order to do the geometric sequences correctly. So, as we can see, our objective here is to find, identify, and apply geometric sequences. This is the part where, again, very good, Joe.
Yes.
I got the bag off, everybody.
Yes.
Yeah.
Yeah.
So, arithmetic. This is the part that bothers me. This is always pronounced geometric. I don't know why on earth they made such a big deal out of arithmetic versus arithmetic. But geometric takes us a step up where we're saying, okay, now we're not going to add or think of it as adding a negative or subtracting anymore. Now we need to see what happens if we start to multiply stuff. So the getting ready says, find the fifth term in each of these number patterns. Can you tell what these sequences have in common and explain your reasoning? I'm actually not going to use the instructions they have. What I want from you is, can you figure out what it is they are multiplying each one of these terms by in A? 2. So if we kept going, the next term would be 48. In B, what are they multiplying by? 21, 1/10. Multiplied by 1/10 because we see another 0 moving here to the right-hand side. How about in C? Negative 1/3. Whenever we see that positive, negative piece, it has to be a negative. That's what we're doing today. So if you're having trouble with that and you're looking at it going, I wouldn't have seen that. Well, if they tell us it's geometric, what we could do is take -1/81 and divide it by 1/27. Just like if we wanted to figure out what they were adding for arithmetic sequences, we could subtract to figure it out. Now, if we want to know what they're multiplying by, we can do division and just use the inverse operation. So a geometric sequence, better get that off of your definition, you're going to need that. A geometric sequence is a sequence of numbers where the ratio means fractions, it means division to us in mathematics, the ratio of the terms with its previous term is constant. Again, it has to be the same thing every time. It can't change up. It has to stay the same. And that is called the common ratio. So this formula is going to have an R in it. And that R is going to be our common ratio. A sequence of numbers where the ratio of a term with its previous term is constant. Can't change. It has to be the same every time. They can't multiply by 1, then multiply by 3, then multiply by 5. I mean, we know those are odd numbers, but that's not a constant ratio. That's why it's called common. They all have to have it. So our sequences are going to look like this, and we are always going to start with the first term. So we'll have the first term, and then to get the second term, you'll multiply it by whatever that common ratio is. And then to get the next term, you'd multiply again by that common ratio, which would make it r squared. And you'll multiply again to get the third term, a sub 1 times r sub 1, r sub 2, r sub, I shouldn't say sub, it's powers. R squared, r to the third, r to the fourth, etc. And we notice these are going up by 1 each time. It's like they're just adding 1 power there, and that's what we would need to do to get those. So recursively, our formula is going to look like this. Here's the first term, start with this. We have to do that with recursive. And then to find any term, take the previous term and multiply it by r for n greater than 1. So again, we're talking about starting with the first term. We're not going to go to the 0 term when we're doing ours. Explicitly, it's to find any term, take the first term times r to the power of n minus 1, where n is greater than or equal to 1. So if we put a 1 in there, notice what happens. 1 minus 1 would be 0, this would become a 1, and we would just get a sub 1, which would be the first term. So those are the formulas, this is the definition, and they need to go on the front page of your packet. So flip it over, find that column for geometric. We want our definition and our two new formulas. So geometric sequence, sequence of numbers where the ratio of a term with its previous term is constant. The formulas are sometimes going to look like they're getting a little more complex, but they actually become easier to use. Here's why. When we did the arithmetic sequences, we had to find two things. We had to find the first term and we had to find d. Well, with this one, it's still two things, but it's kind of like, well, it's only one that's different from what we were doing before. I mean, we're still going to put the first term here, but now we just need to find r. The rest of it stays put. So with the highlighter, what we want to do is highlight the pieces that we're going to have to find. And we obviously are going to have to tell them for recursive, hey, here's the first term. But that's not new to us. It's something we already know how to do. And then we have to figure out what r is. And again, it's common ratio. To find it, what we can do is take any term and divide it by the term before it. And that will give us the common ratio. And then in the explicit, yes, we're again going to find the first term, but we certainly know where to look for that now. And r. The rest of that is just part of the formula. So those are the pieces that we're going to put in for recursive and explicit. And what we're going to do is start with, hey, basic. Do we recognize one when we see one? Then can we write it? And then can we use it? Find anything that's missing, because we need that a sub 1 and r to write these. So our objective, we're going to figure out how to use these geometrics. We're going to define, we're going to identify, and we're going to use the geometric sequences. We have to know them when we see them. We have to. Identifying geometric sequences. Is the sequence geometric? If it is, then what's the first term and what's r? So we'll take it an extra step. So take a look at A. 3, 6, 12, 24, 48. Geometric?
Yes.
Yes. And they want a sub 1 and r. So what's a sub 1?
3.
3. What's r?
2.
Got it. B. 3, 6, 9, 12, 15. Not geometric?
Arithmetic.
How do you know it's arithmetic?
They're adding.
Not geometric. C. 3 to the 5th, 3 to the 10th, 3 to the 15th, 3 to the 20th. Geometric? It is. What's the first term?
Not 3.
What do you multiply 3 to the 5th by to get 3 to the 10th?
What? Close. That was close. I'm sorry, 3 to the 5th.
There you go. 3 to the 5th. It's kind of a weird one, isn't it?
The R and the A sub 1 are the same.
They are. They are. Kind of awkward.
I would make it nice.
So down here we have a wonderful dot. I would like you to investigate those while I get you a candy bar.
Yes.
So you can check and see how you're doing.
Yes.
So A, yes or no? Yes. A sub 1? R,
2.
another one where A sub n and R are the exact
Wow.
same thing. B, yes or no?
No.
No,
It's arithmetic.
it is, isn't it? And 4 each time. How about C?
Yes.
A sub 1
2 to the third.
and R.
2 to the fourth. Oh, I beat you.
One of the four.
All right. So what we had to remember there was when the base is the same, we add exponents to get to the next term. Again, you could do it this way. You could say, if I'm having trouble seeing this, I'm going to take any term and divide it by the previous term. Well, now we can see it. Hey, it's subtraction. It should be 2 to the 4th. So if you don't see it right away, don't stress. Just remember, common ratio means we can write that as a fraction. So down here it says, what are the indicated terms of the geometric sequence? And the good news is they told us it was geometric. And for me, again, the recursive stuff, I just don't bother with it. So they want the 10th term. I'm not going to sit there and multiply by the same number 10 times. That's just silly. You could, but I would really like a formula that would give me any term. So as soon as I see geometric, bam, that's what I'm thinking. And then I remember I need the first term, and I need to figure out what R is. And again, you just kind of in your head say 4 times something is 12. Oh, that something is 3. And I usually put that number that's the base for my power in parentheses. And that's just to make sure that it's kind of sitting there staring me in the face where I can see, hey, it's a 3 that I have to raise to a power. And then they want the 10th term. Well, we've done this before. We need to put a 10 in for n. But what we haven't had to do before is try and raise 3 to the 9th power with our noggin. So that's why we bring the calculators. Geometric is going to make these big fast. It really is. So generally we want to have the calculator handy whenever we're geometric. So we can do 4 times 3 to the 9th power.
Oh.
And the calculator will follow the order of operations even without the parentheses. But yeah, not something that generally pops into
That's
the
a
head.
big number.
It is. Why? Tell your partner why these get so big so fast versus arithmetic.
Because you're multiplying. Well, yeah.
Geometric's multiplying. It's multiplying. So they're going to get bigger faster versus addition. It's going to happen.
Yeah.
So now I believe there's one got it for you. Oh, wait a minute. Not yet. We got to do some more stuff.
Then there's got it after.
Second and third terms of this geometric sequence. Oh boy. Okay, so here's what I have. I know that the first term is 2. That's very helpful. 1, 2, 3, 4. I know the fourth term is negative 54. And yes, if we're good at patterns, we can probably figure this out without using the formula. But, you know, that's not what this is for. The formulas are for situations where we have trouble finding it. So what I do is I think, well, let's see here. This is what I have, and that's the information that I'm going to use to find R. So let's see. I know that a sub 1 is 2. I'll put that right here. There must be some way for me to use this 4 and this negative 54 to figure out what that R is. And there is. This is n. And this is what you get when you put n in. So that means it's going to go over here. And then I'll have my little r to the 4 minus 1 power. Well, usually I wouldn't write 4 minus 1. I'd do 3 this way. But I think we know how to solve that. I'm going to have to divide both sides by 2. And then do cubing, the cube root. Now at this point, we can decide whether or not we want to go back and write the formula, or, well, if r is negative 3, can't we just multiply stuff by negative 3 and see what we get? So we'd say 2 times negative 3 is negative 6, and then negative 6 times negative 3 would be 18, and then we'd just check and make sure that this is going to give us that negative 54 in the end. So 18 times negative 3 will get you the negative 54. So these were the 2 that we needed. And this was just kind of a quick check to make sure that we actually found the correct R. Now, could we have taken this -3, plopped it back up in here with an ace of 1 of 2, and gotten a nice formula for it? Absolutely. If you're a formula person, and there's some of you that are out there, go for it. You definitely can do that, as long as you do the math right with the formula. So, there's one for you. What is the second term of this geometric sequence? Again, kind of do the math the hard way. Don't cheat at this point, and see if you and your partner can come up with that term. First term of 3, third term of 12. So 12 equals 3 times r to the 3 minus 1 would be r squared. Divide. Square root. We get 2. But wait a minute. Square root would be plus or minus 2. So let's take a peek at this. 3 blank 12. Okay, well if we multiply by positive 2, we'd get 6. If we multiply by negative 2, we'd get negative 6. Now, if we keep going to check our third term, we'd say, okay, well, if I multiply by 2 again, I've got 12. Oh, 6 is it. But if I multiply negative 6 by negative 2, won't I also get 12? So because we had to take an even root, and we don't have any more terms, if they'd have just given us one more term, we could tell them for sure which one this was. But we don't know, we have to give them both. We have to give them both. And that's going to be what happens whenever our index up here, whenever our power is going to be even, because we're going to have to take even roots, means we're going to have a plus or minus situation in there. So a little bit different with that one. Now, what else do they want us to learn how to do? Word problem, box and ball, and I am going to keep going today, and that's because tomorrow you've got a quiz, and I want you to have just a teeny bit of stuff left for us to do together as a class and have plenty of time to take a quiz. When a ball bounces, the heights of consecutive bounces do form a geometric sequence. And it says, what are the heights of the fourth and fifth bounces? So, take a look at this and think, okay, well, technically there's my first bounce, so that's going to be 100. So first bounce, second bounce, third bounce. And I realize this isn't really any different than what we were just doing.
Yeah.
It's the same stuff. So we'll put her in the formula and see what we have. Like it says, think the heights of the first and third bounces are given in the picture. We want to use that. We're going to use that explicit formula. We're going to figure out what R is. So, I better put the page since I scrolled too high here. Base of 1 is 100. Base of 3 is 49. So, I'm going to write the formula down again so I don't lose anybody. What's going to go on the left? 49. Equals what? 100. R? And then what do we use for a power? Right there. Oh.
Divide by.
Even if that was reducible, I don't think I'd want to.
No. Oh my God. Because then you can have 7 over 10.
Could it be -7/10? This is a word problem. It can't be.
That's not logical.
So yeah, that's the difference between knowing what the problem is about and just having a formula. So now we go back and say, all right, formula, we got you covered. We know the first term is 100, and we know this should be 7/10 to the n-1. And now whatever they wanted, we could crank out on the calculator. And what did they want? They wanted to know the fourth and fifth bounces. So let's tell them the fourth and fifth bounces.
100 times.
So just make sure you use parentheses for the fraction. We'll be fine. Decimals. They did. It's a word problem, so yeah, they'll give decimals versus fractions. Usually the rule is that we just leave everything as the original problem came, so usually we give this as a fraction answer. And somewhere up there was a label. Was it centimeters?
Yeah.
And then for a sub 5, I'm going to cheat. I'm going to do second enter, pull that one back up, and just put a 4 here instead of retyping the whole thing.
Well, that's great.
24.01. Not that it's really difficult to type it or anything, but once I get it in there right, I'd like to use it again. So there it is. And then in the got it, there's some for you. To find the height of the 10th bounce, would you use the recursive or the explicit formula explained? So talk to your partner, would you do it recursively or would you go ahead and do this with the explicit formula? And then A, you gotta,
Use the
B, you have to find some more.
I just used 4.05.
I
No,
got 0.04.
I got 4.03533607.
Oh, I forgot to multiply by 100. I see.
Everybody have them? I just put for A that I you know my preference anyway, I've already told you, I like explicit. We already had the formula drive, for goodness sake. You just put another number in there. Yeah, it's in my calculator even. All I would have to do is change that last number. So for A sub 6, we're just going to be raising it to the 5th power.
That's crazy.
And then they also wanted the 10th. So the 9th power. So how far did you go decimal wise?
Well, for A to the
went to
10th,
three.
I went
I went
all
to
the way.
the 1,000.
Okay.
I went all the way on A to the 10th.
I went all the way.
I have all of them.
I went to the 10 millionths. 10 millionths.
How about on B?
I went 4.0353607.
And they didn't tell us, so you know we could do whatever. I guess I'm gonna kind of stick with the 3 decimal places that we had for that one and go with 4.035 centimeters. Depends on how accurate you want to be. I mean, we're just talking about a bouncing ball here. Do we really need to go out to millionths or anything
Yes,
like that
we
for
do.
bounce? Yes, we do. Accuracy is that important to
Yes,
you. Okay.
absolutely.
4, 3, 2, 1, 0 me. Identifying and working
3.
with. You bet.
I'm a 3.
Bouncing ball wasn't so bad, even for a word problem, right? That wasn't awful. Okay, great. Thank you, partner. They're wonderful.
Thank you, partner.
Whoa, homework, you say? You're just
There
like,
it is.
you just might not do any homework.
Let's not do any of this.
Never gonna happen. Need the practice. The human brain needs the practice.
Not necessarily, it needs rest.
That's what weekends are for.
No, that's not what it is.
Weekends are for us.
No.
Yeah, passes right over there at one.
I got
File cabinets. That's what it is.